Hey, it's Kelby. In this video, I'll show you how Rock My Retirement performs Monte Carlo simulations. This is more of an under-the-hood video, and you don't need to know this stuff to plan your retirement, but you might find it interesting. So, let's take a look at how it works. Monte Carlo simulations use randomness to generate probability distributions. Wow, that's a mouthful. Let's simplify that and get rid of all the jargon. Most of the menus in Rock My Retirement have graphs that show you in real time how your retirement would hold up in various simulations. These simulations are each based on scenarios. A scenario imagines that your retirement experiences the same economic conditions as some historical period. So, for example, the first scenario may reflect actual inflation, stock market gains, interest rates, etc. from 1926 through 1955. The second scenario would reflect data from 1927 through 1956, and so on. Well, let's suppose that you find that your retirement would hold up just fine in 90% of the simulations. You might be tempted to think that means there is a 90% likelihood that you won't run out of money. But that would be a false conclusion, because not all scenarios are equally likely, and because we have a limited number of historical scenarios. The Monte Carlo method enables us to use a limited amount of historical data to create a very large number of possible scenarios, enough that we can estimate the probability that your retirement holds up over time. Let's dive into how we do that. Let's suppose that you're planning on a 30-year retirement. The first thing we need to do is create random values for every economic condition we want to take into account for every year. Inflation, large cap stock growth, mid cap stock growth, small cap stock growth, bonds, etc. For simplicity's sake, let's just focus on a few of those for now, but Rock My Retirement does everything. In the real world, these values are not completely random. The value in each year needs to be reasonably in the range of what we have historically seen. Let's use inflation as an example. Since 1926, the average rate of annual inflation is about 3%, and the standard deviation is roughly 3.8%. So we use the standard deviation to create different inflation values for each year, with the overall set of values being similar to the historical range, both in terms of the average value and in terms of the deviation from that average. But simply randomizing the data leaves us with a mess of random numbers that are completely independent of each other. And that's not how things work in the real world. In the real world, economic values in a given year are correlated, both to each other and to values in the prior years. So now we need to tweak our random data so that it better reflects the way those correlations exist in the real world. First, we need to account for how different variables tend to correlate to one another in a given year. To do that, we use this fancy thing called a Cholesky decomposition. You do not need to know that term, there won't be a quiz. But the Cholesky decomposition helps us account for the fact that if inflation goes way up in a year, interest rates tend to go way up too. And if large cap stocks have strong gains in a year, then mid cap stocks and small cap stocks tend to have solid gains also. It would be highly unlikely that large cap stocks go up by 20% in a year when mid cap stocks go down 35%. Applying the Cholesky decomposition ensures that sudden spikes or drops in one variable naturally influences other variables the same way it would in the real world. To run the Cholesky decomposition, we first evaluate how strongly each variable tends to correlate to every other variable in the historical data. We use those values to create what we call a correlation matrix. Then, when our randomly generated values for a given year stray from these correlations, we give them a nudge so that the variables reflect these real-world correlations. Now, our random data should reflect the real-world correlations between variables. But we're not done. Next, we need to account for trends that variables follow over time. We do that using something called ARIMA modeling. ARIMA stands for Autoregressive Integrated Moving Average. ARIMA modeling has two components, momentum and mean reversion. Momentum refers to the fact that for some variables, a high value in one year may correlate with a high value in the next year. For example, we know that inflation typically occurs in a multi-year cycle. So, if inflation is high in one year, it will probably still be somewhat high the next year. It would be extremely unlikely that a year with 10% inflation would be followed by a year with 1% inflation. So, ARIMA nudges the values in our random data to ensure that they reasonably reflect momentum-based correlations. Mean reversion refers to the fact that for some variables, high values in one or more years correlate to lower values in subsequent years, so that the average reverts to a mean over time. For example, we know that large cap stocks have a mean total rate of return of about 10.5% since 1926. When we see multiple years that are significantly higher than that, we will eventually see returns drop or fall negative, such that the average falls back to somewhere around 10.5%. So ARIMA nudges the values in our random data to ensure that they reasonably reflect the mean reversion for each variable. Now, our data will reflect the time-based trends that each variable exhibits in the real world. Between Cholesky decompositions and ARIMA, we've done a lot of complex math that results in a lot of nudging, but the end result is easy to understand. We have created a random simulation that experiences the same kinds of twists and turns that happen in the real world. That gives you clear insight into your retirement's resilience. But all of this math only gives us the random correlated data that we need to run one simulation. If we're going to estimate the probability that your retirement holds up, we need to generate many randomized simulations. And how many does it take? Well, that depends on how confident you want to be that you're getting an accurate answer. The simplified answer is that our Monte Carlo analysis becomes more accurate the more simulations we run. So let's assume that a Monte Carlo simulation tells you that you are 95% likely not to run out of money during your retirement. That 95% figure has a margin of error that gets smaller and smaller as you do more simulations. Here's a chart that shows the margin of error that you should expect based on the number of simulations. Keep in mind, though, that this margin of error assumes that the ranges and correlations we have seen over the past 100 years are in fact representative of how our economy will continue to work. It does not account for the possibility that things will change in a way that turns history on its head. An asteroid could crash into the eastern seaboard, or maybe our enormous national debt could cause our economy to collapse worse than what we saw during the Great Depression. If we get a black swan event that is far beyond anything we've seen before, then all bets are off. A Monte Carlo simulation has no way to predict those odds, no matter how many simulations we run. But absent an unprecedented black swan event, Monte Carlo simulations are designed to give us a very high confidence level if we run somewhere between 10 and 50,000 simulations. Now, running that many simulations takes a lot of computing cycles. Software developers know that you don't want to wait a long time while your computer runs lots of simulations, so many retirement planning tools take shortcuts. Some tools will only run 1,000 simulations, which has a higher margin for error. Many use an overly simplified math in their simulations in order to make it run faster. For example, they may use a single type of historical data to return your annual investment returns, such as using the S&P 500's returns to model all of your investments. That has a lot of downsides. It can skew your overall rate of return because different asset classes have different average rates of return. In fact, the S&P 500 has a higher average rate of return than other asset classes, so that can artificially inflate your expected rate of return and maybe be more optimistic about your likelihood of success. On the other hand, it also effectively reduces the number of asset classes in your portfolio, which reduces your level of diversification, and that can artificially deflate your performance. So these kinds of shortcuts can distort the odds. Also, Many tools will simply pick random data without accounting for the various correlations we see in the real world. Maybe they don't do a thorough Cholesky decomposition or ARIMA modeling, and that can also distort your results significantly. But Rock My Retirement does not take any shortcuts. Rock My Retirement has been optimized to run simulations very fast. So each simulation is a complete simulation that accounts for all the data you've entered, all the different asset classes. Rock My Retirement creates separate randomized but correlated values for every asset class in every year. Rock My Retirement runs a minimum of 5,000 simulations, and you may choose to run up to 100,000 simulations with only a modest increase in wait time. This faithful application of the science behind Monte Carlo simulations makes Rock My Retirement a very powerful tool. Well, that does it for the math underlying Monte Carlo simulations, and I hope this tool helps you rock your retirement.